This is a Chapter 8 introduction on linear regression. Now, the chapter starts out talking about the association between protein and fat in grams in Burger King Whopper hamburgers. And so here's the association, and you can, here's the scatter plot, and you can see that it's medium, moderate, positive, and straight. Now, the correlation would be very strong, fairly strong, but where does the line come from? So this chapter is really going to be about the equation. Now, this chapter is going to refer to the equation in this model, in this formula. Y hat equals b sub 0, that's the y-intercept, plus b sub 1 times x, where y hat is the estimated output. Now, it's really important that you equals starting point, whatever that is. That's what y hat equals when x is 0 plus b sub 1 times explanatory variable. Now let's use the terminology. Estimated consequential variable. Let's put it in terms of the book. Consequential variable. So it's consequential variable versus explanatory variable. So in this case, it would be estimated fat equals some amount, we'll call it b sub 0, plus b sub 1, that's the rate of change, times protein. Now the protein is not estimated. It's the protein that's given in the data. So the protein, so we'll talk about this in a minute. But anyway, the protein is the actual X in the ordered pairs. And then the line of best fit is made out of the X from the ordered pairs and then the estimated Y's. And we'll talk about where these estimated Y's come from. Alright, so let's go to the next page. Pretty much we're done with here. I gotta turn this thing off. Go to the next page. Okay. So we can make a model. That's what we're talking about, a model. Okay? And in this, a linear model. That's very important. Okay. And this next page talks about this whole Y hat business. Okay? Also, it brings in the notion, a very, very important idea called residuals. What is a residual? Okay, well, we started out with our actual X and Y values. Now let's look at them over here on the graph. Okay. Now, through some magic, which we haven't talked about yet, we end up with a pair. These are all the points on this. We end up with an estimated output for that Y value that's on the line of best fit, called X comma Y hat. Now the residual is Y minus Y hat equals the residual. And we'll symbolize the residual. We've already used up R. R stands for correlation. So the residual is known as E. E for error. Because models are useful but they're always slightly wrong. Sometimes they're wrong by a lot, but they can still be useful. You just have to remember that, anyway, that they are always, that your predicted values are always going to be slightly off. Okay, now, in calculating the line of best fit, if you take the residuals, think about the residuals, the errors, okay? If you added up all the errors, you would get 0. So we've seen this little trick before. If we take the errors and square them and add them up, then that equals some number, okay? Now, the line of best fit is the line in which the squared residuals is the smallest. Now that would make sense. Now take a look at this line here. Okay, this is the line of best fit. You got some points above it and some below, and it's always going to be equal. But the main thing is that this line creates a set of residuals whose squared sum, you take the residuals, you square them, and you add them all up together, is the least possible number. Now, how is that possible? That seems really amazing. How could that happen? Oops, what the heck did I just do? Let's make this here. Okay. And it's called the least squared residual. And here's the guy, mathematician, these French guys, they're always way out there on math. And of course Gauss, this German guy, he's another big dude. Okay. So how does this happen? Well, it turns out you already know how it happens. How does it happen? I have to turn this off. How does it happen? Correlation. Now, we talked about this a little bit in the last chapter. Remember that all the ordered pairs, we start out with x and y, x sub I, y sub I. Now with that, the s sub I means the first ordered pair, the second ordered pair, the third ordered pair. I is like a little symbol that holds, that stands for 1, 2, 3, 4, 5. It's like a looping symbol. Okay. Now, these ordered pairs are converted to z-scores by means of sliding and scaling. So you take x sub I minus the mean, y bar, we'll call it x bar, well, minus the mean. I get my symbols mixed up. I'm still going to use y bar. It's going to be confusing. Minus the mean divided by the standard deviation. There, let me write this differently. Sorry about this. Let's do it like this. X sub I minus the mean of the x variables divided by the standard deviation of the x variables. Okay, now we're going to do that for every x coordinate. And that's a z-score. And then we're going to take y sub I, in other words, the corresponding y coordinate, and subtract the mean of the y variables, and then divide that by the standard deviation of the y variables. And so what do we end up with? We end up with z sub x sub I, comma, z sub y sub I. So we end up with a set of z-scores. Now correlation, which is the strength of the linear relationship, equals the sum of the product of the z-scores of the linear pairs divided by n minus 1. Now we've been through that. That's last chapter, okay? Now look at this picture here of, this is the ordered z-score pairs of the data from the previous page. Okay, now look at the shape. Here's the actual data. Here's the x and y values. Okay? And you can see the shape of the data and everything. And here is the z-scores right here. Now notice the data has the same shape. Okay? It is the same. The association looks the same. There's no difference in it. It's linear, moderately strong, etc., etc. Okay? So, this is interesting. So we make a scatter plot of that, but notice now that the values are, how they're scattered, and we have a whole bunch in the all four quadrants here, whereas the original picture was only in the first quadrant. Well, that's because we have z-scores that are positive and negative, negative and positive, negative and negative, and positive and positive. Okay, mostly positive and positive because it's a fairly positive association. Okay, so we can talk about the line of best fit for the z-scores, and they do that next in trying to make this explanation. So we can have the estimated z-score of a given y-coordinate equals, well, the origin of this graph when x equals, notice it goes through the origin. So in other words, when x equals 0, y equals 0. So b sub 0 equals 0. So there's no b sub 0, or it's 0. Okay, remember that. That's from Algebra 2, Algebra 1, and everything else. You can see this graph goes through the origin, which would make sense. Why? Because the center of the graph is going to be the mean, which is going to be 0. Remember, when you standardize the data, you are now have a normal distribution of a mean of 0. So the x coordinates, the z scores for the x coordinates have a normal distribution of 0, 1. 0 mean, 1 standard deviation. And the z-scores for the y-coordinates have a normal distribution of 0, 1. So the two means make an ordered pair, 0, 0, right here. Okay, that is the z-scores. So the z-score, the mean z-score for the x and the mean z-score for the y is an ordered pair. It's on the line. So you have an ordered pair of the mean z sub x sub mean, comma, z sub y sub mean. Okay, and that's right there, 0, 0. And so anyway, b sub 0 is 1. So what is the slope? So we have the estimated z-score of y sub I is going to equal something times the z-score, the actual z-score of the x data. Well, what's that going to be? Well, it turns out that slope is r. It's the correlation. So this is extremely interesting. So the whole thing, when you have this sort of basic initial line. Now you can see we're going to make a step from here to, we're going to make the next step to the line of best fit, and we'll see that in a minute. But this is the line of best fit for the z-scores, and so the correlation coefficient is at the heart of, is the slope. Is not at the heart of, it is the slope of the line of best fit of the z-scores of the data. And it makes exactly, notice the line that it makes. The line goes through the data exactly the same as it did on the previous page, right here. And it's going to have, the residuals are going to have a different scale but they're going to be proportionately the same. That is, the errors, the difference between the actual z sub y for a given point and the estimated z sub y, those differences are going to be the same as they are here, proportionately the same. Okay, so where is this taking us? Well, you probably are beginning to suspect that in the actual line of best fit, correlation is going to play a normal role, an enormous role, and that is completely true. So let's scroll down a little bit and see where this is going. Okay. And in fact, we know what the correlation is. So here's our line. We can now write the line. We did linear regression and we got 0.83, but what does this mean? So we calculated the correlation. So we have the estimated fat, the z-score of the fat, equals 0.83 times the z-score of the protein. Now you say, okay, that's great. Okay, it's interesting. Okay. Now, what does this mean? Well, an increase in 1 standard deviation away from in protein will result in 0.83, an increase of 0.83 in the standard deviation of the z-score of the fat. Okay, now if you know the mean and standard deviation of the fat and the proteins, right away you're going to know what all this stuff means. So let's go to the next page. Okay, there we go. So now, come on, don't do that to me. All right, so let's look at these. Why don't you take a look at these questions and see if you can answer them. And then after you check them, the answers to these questions are at the back of the homework questions. Then come on back to the recording and we will continue. So you could stop it, work on these, and then check your answers in the book or whatever. Let me go on. Now, they do a lot of math here, which is, if you're into it, check it out. If you're not, don't worry about it. Okay? But here's the long and the short of it. If you wanted to know where you were with a particular data value in terms of your z-score, so to go from this to the actual line of best fit, you're going to read this paragraph right here. So slope of R for z-scores means that for every increase of 1 standard deviation in z sub x, there is an increase in R standard deviations in z sub y. 1 up over 1 up R. As you probably said in algebra, translate back to the original x and y values. Over 1 standard deviation in x and up R standard deviations in y. So B sub 1, the slope of the actual line of best fit, is going to equal the standard deviation of the y values divided by the standard deviation of the x values times R. Now, you don't have to know how all the math works or anything like that to get here, but it is interesting to go through this box and work it out and all that. But this you need to know, and this you need to know. Okay, plus all the stuff that led up to this. You really need to know this. I mean, you really need to have these ideas in your head to know where this stuff comes from. So now we got the old problem we used to have. What about b sub 0? In other words, the y-intercept, or the y-hat intercept, if you will. So we got b sub 0 plus, let's write this in one last time, the standard deviation of y over the standard deviation of x times r times x. Okay, let's put this in parentheses. Okay, from now on we will refer to this as b sub 1. Well, how do we find b sub 0? Well, just as z for the mean of x, comma, z for the mean of y, okay, which is 0, 0, is on the line of best fit, so too we have an ordered pair that's always on the line of best fit of x bar, comma, y bar. And I'm using x bar and y bar to refer to the means of the x variables and the y variables. So we plug them in to this equation here to get b sub 0. So we get y bar equals b sub 0 plus b sub 1 times x bar. So y bar minus b sub 1 times x bar equals b sub 0. And so this gives you the other term in the line of best fit. And you can see how everything comes, what is the one statistic out of which everything is made? And that is the mean. Why? Because the mean makes the standard deviation. The mean and standard deviation make the z's, and all of these make line of best fit. So line of best fit is really made out ultimately out of the mean, which is why it's so important that the data be normal. That it's okay to use the mean. If it isn't, and in this case it's got to be straight, because so much is derived from the mean. Let's go to the next page. Okay, so this is the regression line in real units. I think we've pretty much got there. Okay. Let's see. I'm going to go to here. And we covered this. Alright. So let's go. Now we'll go here. Okay, and so we do all the math and everything, and they do this here. And we end up with estimated fat equals 6.8 plus 0.97 of protein. Now what does this mean? It means that if you have a hamburger with 0 protein, you're going to have 6.8 grams of fat. And for every increase of 1 gram, because the units are grams, for every increase of 1 gram of protein, your fat increases by 6.8 grams. Okay. So let's see, where are we here? Okay, so here's a good example. It's good to go through this, which I would do. And then it would be good to answer these questions here, 4 through 7. Take a break and do those, and then come back to the recording. Let's look at, this is really important here. I guess all this stuff's important. I keep saying everything's important. It gets tiresome. This is a nice example. I gotta go back to the previous page. A step-by-step example calculating a regression equation. And you need to go through this and really study it. The whole plan, the writing and everything, checking the preconditions, stating what you're trying to find out. Everything on the right side is what is part of your answer. On the left side is a statement of what you're doing in order to produce this answer. So the right side is the actual answer. The left side is what you do to get there. Let's go to the next page. And you would be given the data, and you would make the scatter plot, and then here's your preconditions and as comments on the scatter plot. And this is stuff here that you would be thinking about. Notice they shifted the years to 0 to 25 instead of using 1982 for obvious reasons. And think about how it would change B sub 0. You'd like to have B sub 0 mean something instead of being some crazy, gigantic negative number. I mean, you'd really like to know, especially in this case, since if you do that, if you shift 1982 to be the year 0, then 0 will be part of your domain. And so you know for sure that the y-intercept, that B sub 0 will mean something in your regression. All right. You got the mechanics here. You got to show some calculations. Now, these calculations here, you're listing x bar. This is the mean of the x variables. S sub x, the standard deviation of the x variables. Y bar, the mean of the y variables. S sub y, the standard deviation of the y variables. And here's the correlation. All of this stuff is output from when you do linear regression. Now, well, actually, you'd have to do one variable stats on the x-coordinates and then the y-coordinates in order to get these numbers here. Normally, you're not required to show all this stuff, but they're going through it in this chapter because this chapter is making you study it rather closely. But in this case, you can see how the slope b sub 1 of the equation is made out of the correlation times the standard deviation of the y variables divided by the standard deviation of the x values. And then you can see how the y-intercept is made out of the mean of the y-coordinates minus the slope times the mean of the x-coordinates. All right, let's go to the next page. All right, now here's where the whole notion of the variable, I mentioned this before, residuals are referred to by the letter E. Here's an exercise where you calculate residuals. It's not too bad. I'd recommend doing it. But I want to move on in terms of new ideas that are discussed here. Okay, now let's All right, now here's another idea, namely the residuals. Let's go back real quick and look at the picture of those residuals. Bear with me. Okay. Well, let's look at here. We got a couple residuals. Let's look how they're scattered above and below the line of best fit. So we got some below. Those would be negative residuals. Remember, a residual R equals Y minus Y hat. So the estimated, these would be, so here the actual Y value is smaller than the estimated value. So here we have some negative residuals. Now we got some positives, more positives, then a negative, bunch of negatives, positive, and positive, negative, positive. It kind of zigzags up and down the line in terms of how the residuals are distributed above and below the line of best fit. When you see this pattern where they just kind of zigzags up and down, that's a good thing, because it means that it indicates that the association is straight. When you see something like this, where you have, here's your line of best fit, and the dots, you have some dots going like this. Now sometimes you don't see it right away. This is really obviously curved. But sometimes it's more subtle than this. But then this, you can see, you got residuals, that are above, then below, and then above. Then that indicates that the association is not linear. So this, if you took the residuals and you plotted them versus the x-coordinate, like in this case, they would look like this. They would look like a parabola. Now if you took these residuals and plotted them, so if you did residuals, take the residuals now, not the fat, but the residuals themselves, and plot them versus the x-coordinates, the protein, you would get a random display. And that's a further check that we do. This is a new check. So, here's a whole new precondition now that we're adding to everything else. Okay? The first precondition, your data must be quantitative. Secondly, it must have a linear association. Thirdly, there can't be outliers. Okay, so or you have to make note of them and either leave them in or take them out. And then now once you've satisfied your initial preconditions, then here is, now you run linear regression. You produce the residuals. Now we'll talk about how you do that and how you get a graph like this, because you don't know how to do this yet. But you make a scatter plot of the residuals, and the scatter plot for the residuals must be random. So that's the next condition in order to actually use linear regression. So there's one further condition that you must satisfy before you can actually say you're qualified to use linear regression, and you actually have to do linear regression in order to meet that condition, in order to produce the evidence that it's okay to use it. And that is, you don't get residuals unless you run linear regression. So when you run linreg, in addition to calculating correlation and calculating the z-scores for all the x and y coordinates in order to get correlation, and then making the line a best fit, which we already talked about how it does that, it also makes a list, and it stores it in the calculator, of the residuals for each x coordinate. And so you can use that list to make a scatter plot and then see if you have a truly have a linear regression, if you have a linear association. Okay, now let's do this just checking here. Do this next thing. Okay, and then when you're done with this, take a look at making the standard deviation of the residuals. Now the only difference is you take the sum of the standard of the residuals. So the residuals, I mean, think about it. E equals y minus y hat. So the standard deviation of the residuals equals the square root of the sum of y minus y hat squared divided by, only in this case it's n minus 2. Now the reason for this, you lose 2 degrees of freedom instead of just 1, because you have 2 means involved in order to produce a residual. Well, you have the mean for the x coordinates and the mean for the y coordinates. Okay, so we have now, they also talk about a further assumption. Does the plot thicken? That is, does the scatter plot, does it spread out like this with the fire hose effect, one way or the other? And that's heteroscedasticity. Scedasticity, I don't know how you put it, something like that. Heteroscedasticity refers to the line spreading, having a fire hose effect. That's one more visual check that you make. And you want to see that the residuals have a normal distribution, approximately normal. I mean, this is, you don't have that many residuals with the Burger King hamburgers. So, but if it was heavily skewed or something, you would definitely be worried. Okay, so you look for an approximately normal distribution of the residuals. Fine. Okay, now we get to this next idea, r squared. I'm sure you've been wondering, well, what's r squared all about? Okay. All right. Okay. Here's what you want to remember. It's right here. The squared r squared is the squared correlation. It gives the fraction of the data's variation accounted for by the model. And 1 minus r squared is the fraction of the original variation left in the residuals. Okay, so if your variation is 0.83, that means that 83% of the data's variation, the variation between x and y, is accounted for by the least squares regression model. And 17% is not accounted for. It's left in the residuals, or accounted for by the residuals, if you will. Okay, so the smaller that r squared is, then the less of the variation that is explained by the model. And we use r squared and not r squared adjusted. That's something to look out for. Okay, but you really need to remember this r squared. Gives the fraction of the data's variation accounted for by the model. 1 minus r squared, fraction of the original variation left in the residuals. it's often given as a percentage, and you can look this over. And do this just checking. And then when you're done with this, come on back. And likewise, so remember we used x bar comma y bar as a point, and then we would be using, and then we did y bar equals b sub 0 plus b sub 1 times x bar to produce b sub 0 when we were doing fat versus protein. But if we're doing protein versus fat, then we're going to do x bar equals b sub 0 plus our new b sub 1, which is s sub x over s sub y, times y bar. Okay, so just be aware of that. You can definitely reverse the relationship, one versus the other. That's okay. And the correlation won't change, but b sub 0 and b sub 1 will definitely change. Now, here is another worked out step-by-step example, extremely important. Okay, sugar content and calories in cereals. They start out, as again, everything on the right is what you're trying to show. Now, you don't have the data, but you're going through the preconditions. Outliers, there are no obvious outliers. It's straight enough. Says the plot thickened, condition is satisfied. I want to go back to the previous page for a minute. I want to see if there's any other preconditions that were mentioned here. Okay, they had the first quantitative variables condition. All right, so they satisfied that. So let's go to the next page. So here's the preconditions: 1, 2, 3, 4. All right. Then they list y bar and standard deviation of y, x bar, standard deviation of all of this under the context of what the variables mean, the correlation, then the calculations, and then the conclusion. And then here is a plot of the residuals. But now, one of the things that's going to kind of mess you up, along with everything else, is you're going to look at a residual plot and you're going to think, is that really random? Or you're going to start seeing patterns in it. If you look at anything long enough, you're going to see a pattern. And you just want to look at it, you just want to glance at it. It's either got a pattern or it doesn't. The main thing you're looking for is a very definite straight line or a very definite curve. Really what you're going to be looking for is a curve. So if you don't see a curve, forget it. If you see a Komodo dragon, ignore it. Okay, now here's the calculator stuff. Now, they still do this crazy thing where they're labeling the column titles, changing the names to year and tuition and all of that. But we went through this all in class. The thing that we didn't do, and so I'll go through this in a second, is we didn't go through the residuals, plotting the residuals. But it shows you how to find the residuals here. Then here's what I was talking about. Here's a plot of the residuals. Now, it doesn't look terribly random, but it's random considering that there's not very many data points. The more data points you have, the better idea you're going to have about whether this thing is random or not. So let me show you what I'm talking about. How we already went through getting through the first steps. So let me get the calculator ready, and then I'll resume the lecture. And then the only thing I'm going to show you is how to do the residuals. I'm not going to make you sit through me setting up the calculator. You cold. So the data, oops. I never stopped it. Anyway. Okay, so sorry about that. So the data is back on page 149. So I'm going to put in 0 through 6.